Now, on to standard Haskell classes. Type classes can be a metaphor for classes in object-oriented programming, just as types could be compared to objects. Type classes share a hierarchical structure of inheritance that object-oriented programming classes have, namely in terms of operations and methods. However, types are not objects. Type comparisons are evaluated at compile time, not runtime, making Haskell methods completely type-safe. A better analogy is comparing type classes to interfaces in Java. Type classes, like Java interfaces, define the behavior of the type. When defining a type class in Haskell, it can often be helpful to start by inheriting the base behavior from another type and adding specific functionality afterwards. As we mentioned earlier, constraints restrict what types of parameters are allowed to be used for this class. The equality class, EQ, can contain anything that can be equated. Strings, ints, floats, anything that can be equated with a double equal sign falls under this class. Ord is anything that can be compared. Strings, ints, floats, anything like that. Enum is an enumeration class. It is anything that can be an ordered list. Days of the week, sizes, the alphabet, anything like that. Bounded is an enumeration class that can have a distinct beginning and end. The example above shows that the size class we defined in the enum example has a min bound of small and a max bound of large. Show. Show takes whatever data type and returns it as a string. Anything that can be represented as a string falls under this type. Read is the reverse of show. Anything of the read type is a string that you can read and interpret as the type it appears to be. See our above examples. Read true returns true, even though the input was a string and the output is a Boolean. Derivable classes. The 6 type classes at the top of this slide, EQ, Ord, Bounded, Read, Show, and Enum, are the only 6 type classes in this category. They do not need to explicitly define how each functions operate when creating an instance of one of these classes. Instead, as seen above, you merely write deriving and include the class. Any instance of another class would have to define how each function operates. Please proceed to our next video, where we'll pick up with functors, applicatives, and monoids.